You start with a big star, much bigger than our sun. It lives its life for millions of years, fusing lighter elements into heavier ones. It makes carbon, then oxygen, then silicon. Finally, it makes iron in its core. And that's the end of the line. Fusing iron doesn't release energy, it costs energy. So the star's internal furnace shuts down. What happens next is catastrophic. The star's gravity, which was always trying to crush it, suddenly wins. There's no outward push from fusion to hold it up. The core collapses. It collapses in less than a second. The outer layers of the star come crashing down onto this impossibly hard core. They rebound in a massive explosion. We call this a supernova. It's one of the most violent events in the universe. For a few weeks, it can outshine its entire galaxy. But after the fireworks are over, something is left behind: the collapsed core. If the original star was big enough, but not too big, this core becomes a neutron star. It's a city-sized ball of matter, so dense it's hard to even imagine. A neutron star packs more mass than our entire sun into a sphere maybe 20 kilometers across. If you could take a teaspoon of neutron star stuff, it would weigh billions of tons. It would weigh more than Mount Everest. Gravity on its surface is hundreds of billions of times stronger than on Earth. If you dropped something from a meter high, it would hit the surface in a microsecond, moving at millions of kilometers per hour. So, what's inside one of these things? The honest answer is, we don't know for sure. We can't make one in a lab. A neutron star is a place where our understanding of physics is pushed to its absolute limit. All we have are theories, models, and indirect observations. It's a frontier, but by piecing together the clues, we can build a picture. We can take a journey from the surface down to the mysterious center. Let's start at the top. You might think of a neutron star as a solid ball of neutrons, but that's not quite right, especially at the surface. It has layers, like an onion. The very outermost layer is an atmosphere. It's not an atmosphere like ours. It's incredibly thin, maybe only a few centimeters thick. It's made of plasma, superheated atoms, mostly iron or other heavy elements left over from the star's old life. The intense magnetic fields and temperatures of the neutron star cook this plasma to millions of degrees. Go down a bit, just a few meters. The pressure is already immense. We enter the outer crust. This part is solid. It's a rigid lattice, a crystal structure, but it's not made of normal atoms. The gravity is so strong, it has crushed the atoms themselves. The electrons are squeezed out of their orbits. They no longer belong to any single nucleus. Instead, they form a sea of electrons flowing freely through the lattice of atomic nuclei. The nuclei themselves are packed together in a tight, crystalline grid. These are very heavy nuclei, like iron, but with a lot of extra neutrons crammed inside them. This matter is already mind-bogglingly dense. It's a solid metal, 1,000,000,000 times denser than steel. This solid crust is what we think cracks and shifts during starquakes, causing the glitches we see in the regular spin of some neutron stars. Now we go deeper. About a kilometer down into the star, we reach the inner crust. And here, things start to get truly bizarre. The pressure is now so great that the atomic nuclei can't handle it anymore. They are packed so tightly that they are practically touching. The electrons, which are still a free-flowing sea, are being crushed with such force that some of them are driven right into the protons inside the atomic nuclei. An electron and a proton combine to form a neutron. This process is called electron capture. As this happens, the nuclei become bloated with more and more neutrons. They become unstable. They start to drip neutrons. Neutrons leak out of the nuclei and begin to exist as a free gas, swimming between the packed nuclei. So now you have a mixed solid lattice of extremely neutron-rich nuclei, a sea of electrons, and a sea of free neutrons. This is where physics gets weird. The nuclei don't want to be this close. They are all positively charged, and they repel each other. But the strong nuclear force wants to hold them together. It's a battle between these two fundamental forces. To find the lowest energy state, the matter arranges itself into strange shapes. Physicists call this nuclear pasta. At the top of the inner crust, the nuclei are still roughly spherical. Think of gnocchi. As you go deeper and the pressure mounts, they get squeezed together. They merge and form long cylindrical shapes. This is the spaghetti phase. Go deeper still, and these cylinders fuse into giant sheets. This is the lasagna phase. It's a layered structure of nuclear matter. Beyond that, the roles might reverse. You get tubes of neutron gas running through solid nuclear matter like anti-spaghetti. And, finally, you might get bubbles of neutron gas inside the solid like Swiss cheese. This isn't just a fun analogy. These structures are predicted by complex computer simulations. They are the most stable way for matter to exist under these specific conditions. This pasta layer is incredibly strong, perhaps the strongest material in the universe. But it's a transitional phase. As we keep going down, the pressure keeps rising. Eventually, the pasta dissolves. We have now reached the core. We are maybe a couple of kilometers below the surface. At this point, the atomic nuclei themselves can't survive. They are pressed so hard that they merge together completely. The last remnants of individual nuclei disappear. We are left with a vast, uniform sea of particles. This is the outer core of the neutron star. What's in this sea? It's mostly neutrons. About 95% of the particles here are neutrons. This is where the name neutron star really makes sense. But it's not just neutrons. There is still a small percentage of protons and electrons all mixed together in a kind of charged soup. This mixture is crucial for keeping the star stable. If it were only neutrons, they would decay back into protons and electrons. The presence of the other particles creates a stable equilibrium. But this isn't a normal liquid. The temperatures are still hundreds of millions of degrees, but because the density is so high, this is actually considered cold for nuclear matter. Under these conditions, quantum mechanics takes over. The neutrons are expected to form a superfluid. What is a superfluid? It's a state of matter with zero viscosity. It has no friction. If you were to stir a bucket of neutron superfluid, it would spin forever. It could flow without any resistance. At the same time, the protons in the mix are expected to form a superconductor. A superconductor is a material with zero electrical resistance. An electrical current started in, it would flow forever without losing any energy. So the outer core of a neutron star is likely a bizarre quantum liquid, a mixture of a neutron superfluid and a proton superconductor, all intermingled with a sea of normal electrons. Because the star is spinning, often hundreds of times per second, the superfluid wouldn't just sit there. It would form tiny, quantized vortices, trillions upon trillions of microscopic whirlpools, all aligned with the star's axis of rotation. These vortices are thought to interact with the star's solid crust. Sometimes they can get pinned to the crust's crystal lattice. As the star's spin slowly decreases over time, tension builds up. Suddenly, the vortices can unpin all at once, transferring their rotational energy to the crust. This is our best explanation for the pulsar glitches, the sudden speedups in a neutron star's spin that we observe with radio telescopes. It's a piece of evidence that this superfluid core really exists. So far, our journey has been through territory that most physicists generally agree on. There's an atmosphere, a solid crust, a layer of nuclear pasta, and an outer core made of a neutron superfluid. But now we go to the very center, the inner core, and here all bets are off. The pressure at the center of a neutron star is the highest we know of anywhere in the universe outside of a black hole. It might be a quadrillion times the pressure at the center of the Earth. What happens to matter when you squeeze it that hard? We enter the realm of pure theory and speculation. There are several competing ideas. One possibility is that it's just more of the same. The inner core is simply a denser version of the outer core, a sea of neutrons, protons, and electrons. The matter is stiff enough to resist collapsing any further. The neutrons hold their ground. This is the most conservative model. It doesn't require any new physics we don't already know. The star is just a giant ball of neutron, rich matter all the way down. But many physicists think something more exotic must happen. The energy of each particle is so high that new, strange particles might be created. In our normal world, matter is made of protons and neutrons. Protons and neutrons are made of smaller particles called quarks. There are different types of quarks. Protons and neutrons are made of up and down quarks. But there are other, heavier types. One of them is the strange quark. Under normal conditions, it takes a lot of energy to create particles with strange quarks. They are unstable and decay almost instantly, but in the crushing pressure of a neutron star's core, the situation might be different. It might actually be more energy efficient for some of the up and down quarks inside the neutrons to transform into strange quarks. This would create a soup of new particles called hyperons. Hyperons are like heavier cousins of protons and neutrons. So, one theory is that the inner core is a hyperon soup, a mix of neutrons, protons, and a whole family of these new hyperon particles. If this happens, it has a big consequence. Creating hyperons softens the matter. It makes it more compressible. Imagine squeezing a box of hard marbles. It's very stiff. Now imagine that when you squeeze, the marbles can transform into smaller, softer balls. The whole collection becomes easier to crush. The same thing happens here. If hyperons can form, the core of the neutron star becomes softer. For a given mass, the star would be smaller and more compact than a star made of only neutrons. There is another, even more extreme possibility. What if the pressure is so immense that the neutrons and protons and even the hyperons themselves are destroyed? What if they are squeezed so hard that they break apart and their constituent quarks are set free? If this happens, the core would no longer be made of individual particles like neutrons. It would be a new state of matter entirely, a quark-gluon plasma, a dense, hot soup of free-roaming, up, down, and strange quarks, all held together by their force-carrying particles, the gluons. This would be the ultimate cosmic pressure cooker. It would be matter deconstructed back to its most fundamental building blocks. This quark matter would be even softer than a hyperon soup. A neutron star with a quark matter core would be even smaller and more compact. Some theories take this idea a step further. They propose something called the strange matter hypothesis. This idea suggests that matter made of an equal mix of up, down, and strange quarks, so-called. Strange quark matter might not just exist in neutron star cores. It might be the most stable form of matter in the entire universe, more stable even than the normal matter that makes up you, me, and everything we see. If this is true, then a neutron star with a quark core could trigger a conversion. The quark matter in the core could start eating the neutron matter around it, converting it layer by layer into more strange quark matter. This process could transform the entire star. It would no longer be a neutron star with a quark core. It would be a quark star, or a strange star through and through. It would be a single gigantic nucleus, a city-sized particle made of trillions of quarks. It might not even need the crushing gravity to hold itself together. Chunks of it could be stable on their own. This is a wild idea. It would mean there are two types of compact stars, neutron stars and strange stars. They would look very similar from the outside, but their insides would be fundamentally different. So far, we have no definitive evidence for strange stars, but it remains an exciting possibility. So how do we figure out which of these ideas is right? How do we peek inside a neutron star? We can't use a telescope to see inside. We have to be clever. We have to look for clues in the things we can measure. The two most important clues are a neutron star's mass and its radius. If we can accurately measure the mass and the radius of the same neutron star, we can calculate its density. And its density tells us how stiff the matter inside it is. This stiffness is what physicists call the equation of state. It's a set of rules that says, if you squeeze this stuff with this much pressure, this is how dense it will get. Each of the theories, the simple neutron core, the hyperon soup, the quark matter, predicts a different equation of state. A stiff equation of state, like the one for pure neutron matter, means the star resists being crushed. It will be larger for a given mass. A soft equation of state, like for quark matter, means the star is more compressible. And it will be smaller for the same mass. So if we can measure the mass and radius of many neutron stars, we can plot them on a graph and see which theory's predictions they match. Measuring mass is the easier part. If a neutron star is in a binary system with another star, we can use Kepler's laws to calculate its mass very precisely. We've found many neutron stars, and they all seem to have masses between about 1.2 and 2.2 times the mass of our Sun. That upper limit is important. There is a maximum mass a neutron star can have before its own gravity overwhelms it, and it collapses into a black hole. Where exactly that limit is depends on the equation of state. A stiffer core can support more mass. Finding very heavy neutron stars, ones over 2 solar masses, already helps us rule out some of the softer models, like the simple hyperon soup theories. Measuring the radius is much harder. A neutron star is tiny and very far away. It's like trying to measure the size of a sugar cube in another country. But we have ways. One method is using X-ray telescopes. Neutron stars have hotspots on their surface that emit X-rays as they spin. By carefully analyzing the light from these hotspots and how it is bent by the star's immense gravity, we can get an estimate of the star's radius. A NASA mission called NICER on the International Space Station is doing exactly this. Its results so far seem to point towards a radius of about 12 to 13 kilometers for a typical neutron star. The biggest breakthrough has come from gravitational waves. In 2017, the LIGO and Virgo observatories detected the ripple in space-time from 2 neutron stars spiraling into each other and merging. This was a monumental event. As the 2 stars got closer, they were stretched and deformed by each other's gravity. The extent of the stretching, which we could see in the gravitational wave signal, depended on how stiff the stars were. A stiffer star is harder to deform. The data from that one merger gave us our best constraint yet on the neutron star equation of state. It ruled out both the very stiffest and the very softest models, narrowing down the possibilities for what lies inside. Another clue comes from how neutron stars cool down. A brand new neutron star is incredibly hot, but it cools over time by radiating neutrinos from its core and photons from its surface. The speed of this cooling depends heavily on what the core is made of. A core with a neutron, superfluid, or exotic particles like hyperons or quarks would cool much faster than a simpler core. By finding young neutron stars and measuring their temperature, we can test these cooling models. So where does that leave us? We have a pretty good picture of the outer layers. A solid crust, probably with a bizarre pasta layer beneath it. We have strong evidence for a large liquid core, and good reason to believe it's a quantum superfluid. But the central mystery, the nature of the inner core, remains. The evidence from gravitational waves and heavy neutron star observations seems to disfavor the simplest, softest models. It suggests that whatever is in the core, it has to be pretty stiff. This doesn't mean quark matter is impossible. Some newer models of quark matter suggest it could be very stiff, almost as stiff as neutron matter. It could be that the transition from neutron matter to quark matter only happens in the very center of the most massive neutron stars, right before they collapse into a black hole. What we're looking at inside a neutron star is a phase diagram of matter. Just like how water can be ice, liquid, or steam depending on temperature and pressure, nuclear matter can also have different phases. A neutron star is a natural laboratory that explores these phases. As you go from the crust to the core, you are journeying through increasing pressure, seeing matter transform from a solid crystal to pasta to a neutron liquid, and then to what? That what is one of the biggest open questions in astrophysics and nuclear physics. The answer is locked inside these tiny dead stars scattered across our galaxy. They are the densest, most extreme form of stable matter we know. They sit on the dividing line between a star and a black hole on the edge of oblivion. To understand what's inside them is to understand how matter behaves when it is pushed to the breaking point. And every new observation, every gravitational wave detection, every X-ray measurement gets us a little bit closer to peeling back that final layer and seeing what's at the heart of a stellar ghost. The quest is not just about understanding a weird type of star. It's about understanding the fundamental rules that govern our universe.